we're on section 14.7, and we're going to be talking about converting triple integrals to other coordinate systems. So we've already done doing double integrals into polar coordinates. So now what we're going to do is triple integrals into either cylindrical or spherical coordinates. So we can kind of recall what those two coordinate systems looked like. So cylindrical is basically polar coordinates, just with the z component still staying the same. So you've got that x is our cosine theta, y is our sine theta, and then z is z, r squared is x squared plus y squared, tangent theta is y over x. And we've got the little picture of what all those stand for point in 3 space over there. So we've seen that one before, and then we've seen spherical coordinates. So spherical down here, remember, is we've got rho, phi, theta is our 3 coordinates that we have. So rho is the length of the segment from the origin to the point, and we do restrict that to be a positive length, which is not always the case for r with polar. We did allow for negative r values in polar, but not in spherical. We're going to restrict it to be positive or 0, so not negative. And then phi is the angle between the positive z-axis and that line segment, and phi is restricted to be between 0 and pi, so we'll never consider a half turn for phi. And then theta is the same theta as above, so theta then is the angle that if I dropped this down into the xy plane, theta would be kind of that angle that it swings around the z-axis. So then to switch back and forth, we have that x is rho sine phi cosine theta, y is rho sine phi sine theta. So basically it's like r is getting replaced with rho sine phi in both of those, and then z is rho cosine phi. All of those do just come from those trig formulas, looking at triangles in that picture over there if you want to give it a try. Find the right angle triangles and find all those trig identities. And then we've got that rho squared is x squared plus y squared plus z squared, which you can recognize as the equation of a sphere, because if rho is a constant, it's just going to trace out a sphere in spherical coordinates. So what we're going to take a look at now is how do we convert an integral into these. So if you remember when we did polar coordinates, we had to adjust the bounds based on the region by taking a look at the function. We also had to change the function by subbing in different values for x and y and things. But then we also had an extra scaled factor inside the integrand to make the transition accurate. And so what we're going to end up seeing here is the goal of this is to simplify things by either switching into cylindrical or spherical. So let's talk about how to do it first, and then we'll talk about when or why to do it. So in cylindrical, and the order of integration you could choose in a different order. This is just a common order for it to be done. So a lot of times we put d theta on the outside and then dr on the inside, which is basically the same that we did with polar. And really, in a way, we sneakily did cylindrical coordinates in the past, because we had some triple integrals where we would do the first innermost integral, which was with respect to z, and we would still leave it in terms of x's and y's, and then we would switch to polar coordinates. But that's basically the same as just switching to cylindrical, right away. So what we're going to do is we'll have like our d theta integral on the outside, dr integral in the middle, so that would be like a function, r is a function of theta to a function of theta, so like g1 of theta to g2 of theta. And then for the z functions, rather than waiting to switch them, we're just going to switch them now in the bounds of the z integral. So we've got some function h1 of r cosine theta, r sine theta, so that would have been like a function h1 of xy, and then we're going to go to a second function of what would have been xy is now going to be r cosine theta, r sine theta, and then inside the innermost function, the integrand function, again, we replace x with r cosine theta, y with r sine theta, z just stays z if it does happen to be in there. And then remember that this one actually is the same factor that we had for polar. So we have an r. So we have to multiply by an r. So now we get an r, and then it'll be dz dr d theta. So you can kind of remember that r dr d theta for polar is similar to cylindrical. And then for spherical, again, you don't have to do this order of integration, but oftentimes, a lot of times we do the theta integral on the outside, then the phi, then the rho. So it's basically just your bounds for theta, your bounds for phi, your bounds for rho, and remembering the idea that the innermost integrand or integral bounds could be functions of the outer two. This, like phi, could be a function of theta, but then the outermost one should be constant. And then we're going to do all the replacements. So x in our function f is replaced with rho sine phi cosine theta, y is rho sine phi sine theta, and z is rho cosine phi. So we'd have to kind of remember those conversion formulas. And then with this one, our scale factor is a little more, so we end up with a rho squared sine phi. So we have to have a multiple of the function times rho squared sine phi in order to convert to spherical coordinates. So then, based on this order of integration, it would be d rho d phi d theta over there. So you could, in theory, do those bounds in a different order. Regardless, though, with either of these, regardless of the order of the bounds, you need the same scaled factor in there. And if you're really wondering, I mean, at this point, it kind of feels random as to where those are coming from. That's what we're actually going to explain in the next section, our second section for this week. So when we do 14.8, we're going to explain where those factors came from. Now, just thinking about when you would switch these over, it's pretty similar to the ideas that we had for polar coordinates. So switch to cylindrical coordinates if cylindrical coordinates seem easier. So if your region has, or your functions that you're dealing with have to do with things that really have those kind of circular cross sections. So cylinders, cones, anything like that, really paraboloids work well. Basically anything that has kind of those x squared, y squareds in it. And your region R for these outer two integrals, that region in the xy plane is somehow circular in nature, is going to be useful. For spherical, a common things to do with that is things like spheres. Kind of seems natural. Cones also are pretty simple in spherical coordinates as well, so cones can go to spherical easily. But really, you'll kind of see it based on, again, either representing the graphs, or it's really going to simplify that integrand formula. So we're going to do several examples where we take a look at conversions. So we'll either purposely do a conversion or see why we would want to do a conversion. So that's what we'll do next. We'll do some of them on the board, and we'll do some of them on the computer screen, doing screencast. So you can hop onto those videos next.